Yeah, please go ahead, Stephen.
Great, thank you very much. Hola everyone, it's a real pleasure to be able to present to you today, all the way from the other side of the world in Brisbane, Australia. So, as Flavio introduced, I work for Cisco as well as a wireless technical solutions architect, covering both Australia and New Zealand territories. I only recently joined Cisco about 3 months ago. Prior to that, I was working with Ekahau Wi-Fi Design, who you've probably heard of with site survey design and tools. So I was the systems engineer for Asia Pacific for Ekahau. And prior to Ekahau, I was a principal engineer at Dimension Data, so one of the conference sponsors, which we're very grateful to have here. So I've had quite a broad background across networking, as well as focusing on wireless for the past probably 6 or 7 years. And as you know, like Gustavo, I was in San Diego last week for CWMP Wi-Fi Trek, where I had the pleasure to present there as well. I've still got my my T-shirt on from Wi-Fi Trek that I'm wearing today. So if you ever want to get in touch with me, I've got some contact details up on the slide here. I have a blog at wificoops.com. And you can reach me on Twitter at Stephen__Cooper. Next slide, please, Flavia. Great. So today we're going to be talking about Wi-Fi calling. So have you ever been in the situation where you've got your phone out, you're looking there, you're trying to make a phone call, you can see that you don't have many bars of reception on your phone, and you're trying to call someone, it's just not going through, and you're getting frustrated as to why the call won't go through, and it just disconnects or it times out. Maybe the call does go through, but you've got one-way audio, or it drops out, and you have to hang up and try again. But the whole time you're looking and your Wi-Fi signal is full strength. You know that you've got a good quality Wi-Fi network. So that's why Wi-Fi calling comes in. It's basically using our smartphones to enable us to make cellular calls in areas of poor cellular coverage. So hence the dude, where's my signal up on the screen. So we're basically talking about the ability for our smartphones to be able to use the Wi-Fi connections that we have available to us and then transport those calls across the internet to the carrier. So we're not talking specifically about voice over Wi-Fi, but we're going to be touching on voice over Wi-Fi because there are a lot of design considerations that are relevant for both Wi-Fi calling and voice over Wi-Fi. You know, it can be confusing. Sometimes the Wi-Fi Alliance will specify Wi-Fi calling is everything voice over Wi-Fi, including WhatsApp or Facebook calling or Skype, but those are separate applications. So let's just consider that Wi-Fi calling is a separate application on our device that we need to cater for on our wireless networks and design our wireless networks accordingly for that. So we will discuss what is Wi-Fi calling, what are the benefits of Wi-Fi calling. We'll just briefly cover some of the carriers that support Wi-Fi calling, both in your regions in Latin America as well as globally. We'll also have a look at, you know, what considerations we have around device support and how you actually enable Wi-Fi calling on your devices and what other intricacies there are in the background that we need to consider. And then we'll actually take a look at the establishment of Wi-Fi calling. So how does this device actually securely establish a connection back to your mobile carrier to actually facilitate Wi-Fi calling? So we'll take a bit of a look at some packet captures and analyze some of the frames exchanged for that process and the security behind that. And we'll go into a little bit more detail around listen intervals and some considerations there. So I'll bring up some content that was discussed in another presentation at Wi-Fi Trek last week, which was very useful. And lastly, we'll round it out with just some good best practice design considerations for not only Wi-Fi calling, but voice over Wi-Fi deployments in general. So next slide, please. So essentially, Wi-Fi calling is a carrier offload feature enabling cellular calls in areas of poor coverage. So this could be a retail shopping center, it could be an office building, but picture an environment where there's a lot of times I've seen office environments where a carrier just doesn't put in extended coverage with a distributed antenna system. Maybe they just don't want to pay for that for their subscribers. Maybe it just hasn't been enabled in a building. I've deployed Wi-Fi to many greenfield environments where the distributed antenna system doesn't get switched on for 6 to 12 months after people have actually moved into that building. So if you're talking about a high-rise office building, sometimes that cellular coverage just doesn't get into there in some areas. So this is where we can sort of extend the mobile network operators and the mobile virtual network operators coverage, consider extension of that last mile coverage via the Wi-Fi network. So the technology is referred to being a generic access network, and that's what I was saying earlier. It's basically using the Wi-Fi and the internet to transport, your voice packets to and from an evolved packet data gateway on the carrier's core, instead of going via a cell tower. So this is something that the carrier needs to support. You can't use Wi-Fi calling without the carrier supporting it. So we are seeing more uptake and more demand for Wi-Fi calling, not only in my region down here in Australia and New Zealand, but I've definitely seen more uptake of it across Asia Pacific. And based on feedback from last week's Wi-Fi Track conference, I've definitely heard from a lot of Wi-Fi practitioners that they're getting a lot of requests from their users, and it really depends on your environment, how locked down your environment has to be, whether you can support this sort of application, and that's where the security discussion comes into it. Next slide, please. So I love this diagram. It's quite simple. It's a nice block diagram which shows the components of our smartphone devices on the left-hand side. So the components that make up the phone calling side of things. So you have your RTP protocols and SIP protocols, and on the top part of that path along there, we can see it gets wrapped up into IPsec before it goes over the Wi-Fi, and then from the Wi-Fi it goes over the internet across to the evolved packet data gateway, the EPDG there on the carrier core network, and then it's handled through the carrier core network, and your cellular call will just go back across, whether it's the same carrier, whether it goes across to another carrier's network. That all happens the same as it does with normal cellular to cellular calls. That's all seamless to the user. And then the traffic comes back across that same path using the internet and returning back over the Wi-Fi back to your device. Obviously, if you were not using Wi-Fi calling, or you hadn't had it enabled on your phone or your network, or the carrier didn't have it enabled, it would use that bottom path, just going over your traditional LTE network back into the carrier core. So next slide, please. So what are some of the benefits of Wi-Fi calling? So we have touched on this already. It's the ability to make and receive cellular calls in poor coverage areas. So I've even seen scenarios where a carrier might have a cellular outage in a CBD area, like a central city area, and that might last for 8 hours. And you know how people are tied to their devices these days. As soon as they can't access things on their devices, whether it's Wi-Fi, we get plenty of complaints about Wi-Fi, but even if the cellular connection goes down, people are going to complain and they feel lost without it. So it gives you the ability for some redundancy or an extra way to facilitate cellular calls if you have an outage, or if just as simply the coverage is poor. So another benefit is it's a fairly seamless smartphone experience these days. We've gone through different iterations of iOS and Android platforms for different handsets, but for the most part, it is quite easy to enable Wi-Fi calling on your device and have it work pretty seamlessly. And that's kind of key about these sorts of Wi-Fi technologies and smartphone features and things that people get used to in the home as consumers. Wi-Fi calling is basically one of those consumer features that carriers want to take advantage of, and they've made it available for people to use at the home. And just like anything that you use at the home, whether it's an IoT device, whether it's your Amazon Alexa, whether it's your Apple TV, as you probably well know, bringing those devices and those technologies into enterprise networks can be a real challenge because there's so many other considerations you have in terms of support for protocols, support for the security, support for quality of service. So that's where we need to make sure that, yes, we can have the seamless experience on this side of things, and the carrier can have the seamless experience on that side of things, but we need to make sure that the Wi-Fi provides that seamless experience as well.
Yeah.
So there's
Yeah, can I make a question?
Of course.
All right. So you mentioned in the second topic, seamless experience, as you were explaining, and there is a fine print there saying some carriers require an app. So
yes.
What the carriers are doing today, are they able to do all the configurations only based on the operational system of the devices, or do you still have to have an app, as you mentioned there, to have a seamless experience?
It is carrier and also device dependent. So, for example, my carrier, Telstra, that I use in Australia, you've probably seen similar things on your phones where you might get a carrier settings update will pop up on your phone, whether it's a Samsung Galaxy or an iPhone. That's, one step for a carrier to push out that configuration to your phone to tell the phone, yes, this carrier can support it, and then also tell the phone, how is it actually going to use Wi-Fi calling? How is it going to authenticate? So that's why some carriers or phones require a separate application. It's usually because of the authentication side of things. The carrier doesn't support it, natively within the phone. So we'll touch a little bit more on the security and authentication side of it in a couple of slides' time. But for the most part, on iPhones and Android phones, it's usually just the enabling a radio button, as long as the carrier has pushed out that support in the cellular profile.
Okay. All right.
Cool. So one other advantage, again, it's very carrier dependent as to whether they want to make some money off you while you're roaming overseas. But there is the potential for you to have local rates or even free calls while you're roaming. So Telstra is a pretty good carrier, and they have some good mobile roaming plans, but they don't let me use Wi-Fi calling when I'm traveling overseas, unfortunately. But I know there's some carriers in Europe that do allow it. I think it's either AT&T or Verizon in the US allow it. But again, that's where it's very carrier dependent. So we'll talk about that a little bit more as well. Another benefit is high definition voice calls. So basically, Wi-Fi calling came around when voice over LTE was being introduced as a standard. So that standard for voice over LTE was defining high definition audio quality over your 4G calls. If you were doing a 3G call, it's not classed as high definition. It still sounds good, but that's not a high definition voice call. So Wi-Fi calling is designed to be an extension of voice over LTE, and it's going to give you that high definition call experience. And lastly, we've touched on this before, enhanced indoor coverage for mobile network operators. So you've probably seen a few Wi-Fi vendors having some add-ons and modules that they can put onto access points. I've seen airports which have got Cisco Wave 1 access points with little 3G small cell modules on them. So that's one method that a carrier could utilize Wi-Fi infrastructure to put a 3G small cell module on an access point, but it hasn't been a very popular uptake. It's not been as attractive for a mobile network operator to have that, because they have to relinquish some control over to whoever's managing that Wi-Fi network. Okay, next slide, please. And feel free to click through on that one a couple more times. Thank you. So this is a listing of some of the carriers that do support Wi-Fi calling. So I believe it was T-Mobile as well as Orange in Europe were one of the first carriers to actually offer this as a service to their subscribers. But the uptake has rapidly increased since about 2010, 2012. It's become more and more available as these carriers have been rolling out voice over LTE services. So each carrier is different, and even the mobile virtual network operators are depending on their carrier that they're reselling through to actually have support for voice over LTE. So I know Telstra here in Australia had 4G data way before they had voice over LTE. It took them probably another 18 months to enable voice over LTE and actually have that there enabled on their network before it was ready. And some of these carriers that you see on the screen in front of you, technically they're still operating Wi-Fi calling under a pilot program, even though it's been around for maybe 4 years or so. So you have to be careful. You'll be able to find information from a lot of these carriers on their websites. They will have some instructions on how to enable it on your device, and some of them go into a bit more detail around, you know, how it actually works on their network. And I have a couple of links in a few slides times, but definitely the ones that I'm familiar with in Asia Pacific on the bottom right hand side, Telstra in Australia, NTT Docomo in Japan, Singtel and Optus in Australia and Singapore, you know, they definitely have been supporting Wi-Fi calling for a long time. And I know people that I spoke to at Wi-Fi Trek last week over in North America, they've been using it over on you know, Sprint and Verizon and AT&T and T-Mobile. So it's definitely getting out there.
Yeah, I was thinking here in this audience there are people from some operators like BT, but BT
Yep.
doesn't have how do I say an operation, a cell phone operation here in Brazil.
Right.
As far as I know, and we're expecting people from Porto Seguro in the meeting as well, but I think they didn't show up yet. I don't know if there's anybody
Right.
from Porto.
Yeah,
So,
well, that's the thing. Like BT has a lot of presence globally. You know, they're in Australia, they're in Singapore, but as you say, they're not providing cellular services. They're not even a mobile virtual network operator. They're providing other service provider offerings. You know, whether it's, you know, international connectivity or whether it's, you know, data center or whether it's managed services. So yeah, so it's funny. So even some of the carriers that you've got up there, like even Orange, you know, in Europe, Orange definitely support it. But when you extend Orange across the rest of the world, they don't necessarily support it everywhere. Same with Vodafone. Cool. All right, next slide, please.
And in this
Sorry.
sense, are the operators like cooperating or doing like roaming between their networks to provide like a more worldwide Wi-Fi calling coverage, or not really?
I don't believe so, because that's not really. I mean, where it comes back to, you know, the calls are coming back into the carrier's core network. It's treated like a traditional cellular core, and it's handled through that way normally. So if you've got a, you know, a Telstra to Telstra call, that's going to be all within the carrier's core network. But if you're doing a Telstra to Vodafone call, it's exactly the same in the back end. Once it's gone outside of the EPDG, it's just the same as a normal call. So you wouldn't really be roaming from, you know, Wi-Fi calling on an access point with Telstra to Wi-Fi calling on another access point with Vodafone, because your phone is, I mean, if you've got dual SIM, it actually raises a good question. I'm not sure how dual SIM Wi-Fi calling works. I cannot find any information on it. So that would be something that we could probably look into and see, you know, how would a carrier handle a dual SIM phone with Wi-Fi calling? Would it be able to enable it on both SIMs for that roaming scenario? But in terms of Wi-Fi roaming, that's going to be up to your Wi-Fi infrastructure.
All right. Thank you.
No problems. Next slide, please. Great. So device support. So as I mentioned, it's been enabled on Apple devices for quite a while and Android devices. So iOS 8 or higher on iPhones. Not all Android devices support it. So as you know, there's lots of flavors of Android devices. There's cheap ones and there's high-end ones. Samsung Galaxy, they definitely support it on the S9s. But if you look at some of the cheaper, you know, Galaxy Express phones or like the J models, they don't support Wi-Fi calling. So it really depends on the hardware. It depends on the chipsets inside the phones. That's where it's good to check on your carrier's website to see what sort of devices they support. your carrier should provide a list of devices that they've confirmed to work with Wi-Fi calling. If they don't, then you probably need to get in contact with them and say, hey, I've got this device, will it work with Wi-Fi calling on your network? So I have an image there on the right-hand side. That's literally how easy it is in Australia to enable Wi-Fi calling, is just hit the radio button to say enable Wi-Fi calling on this phone, and up pops Telstra Wi-Fi call. So very easy. There's one bullet point there under enabling Wi-Fi calling saying that one of the regulatory requirements in the US with the FCC is they actually require tracking of emergency call address locations. So despite your smartphone being a roaming and mobile device that you could go all across the world with, the FCC requires you to put in your home address when you enable Wi-Fi calling, because you've probably seen it. You've probably been on Wi-Fi or an internet connection and you've had location enabled on Google Maps, but your location is based on where that internet service is provided. So your location might pop up, all the way across town, or maybe in a different city altogether. Whereas cellular location is a lot more accurate for emergency purposes. They can triangulate your signal and locate you better off cellular signals if they need to. So if you're not using cellular and you're using Wi-Fi and you need to make an emergency call, the FCC has that requirement to enter your call address requirements there when you enable Wi-Fi calling. And that could be the case as well with other regulatory domains. I'm not sure if that's a requirement in South American regulatory domains. You might have some more experience with that than I do. But I've put a few links in there. Telstra, Verizon, and AT&T have some good general guides on Wi-Fi calling, obviously designed at their customers for their networks. But they do have some good information there if you want to read through and see what sort of devices are supported and the process that they have for enabling Wi-Fi calling.
Hey, Stephen, can you hear me?
Sorry?
Can you hear me? So I have a question.
Yes, I can.
You're talking about enable that thing in your home. How this thing's working on enterprise environment? There's any kind of KOS, something like that, to set up that?
Fantastic question. Fantastic question. That's exactly what we're discussing in the upcoming slides.
Oh, okay.
Bear with me, we'll get there. You just summed up the whole purpose of this presentation, so good question. Cool. Next slide, please. So I've put up some additional slides in here compared to what I had at Wi-Fi Check last week, because one of our other presenters that we had last week, Mark Williams, he's based in San Francisco Bay Area. He's got a huge amount of experience in healthcare and retail Wi-Fi deployments supporting voice over Wi-Fi, and he did a fantastic presentation on power save mechanisms. So the Wi-Fi Trek presentation slides are available for the public now to look at, but the actual recording of the sessions probably won't be out until January. But I highly recommend watching his session because he goes into some really good detail about different power save mechanisms and how these devices actually, aim to save battery and what are some of the challenges with that. So what I wanted to do is call out one of the quotes that he had in his content. He mentioned it around Wi-Fi calling, but this is actually applicable to any voice over Wi-Fi application. He basically said, be cautious. Tell your people or your contacts, if you're using Wi-Fi calling, don't call us, we'll call you. So he just raised the concern around inbound calls with Wi-Fi calling and voice over Wi-Fi in general. You're going to have more success with outbound calls from your phone, and there's actually a chance that you might miss inbound calls. So why is that? So we need to understand all of our devices, whether it's laptops, smartphones, dedicated voice over Wi-Fi handsets like Cisco 8821s or ASCOM phones. We need to understand how they actually handle power saving. And especially with smartphones, the sleeping behavior can be completely different when the screen is locked and it's asleep compared to when you've actually got your phone unlocked. Your sleep behavior and the way that your phone actually communicates with the Wi-Fi network can be completely different in those two different scenarios and different in terms of how it handles incoming calls. So what Mark actually was discussing was the listen interval. So the listen interval, basically, the device tells the AP what its listen interval is in its association request. So it's a hexadecimal field, and when it actually translates into a decimal integer, it's telling the AP how often it's going to wake up to check that it's actually got some buffered frames saved for it while it's been asleep, for how many microseconds that it's been asleep for. So this is device dependent. Every device can be different. So I'll show some examples on the next slide, but you need to keep in mind that some devices can actually have a long listen interval, which can actually result in misframes. So basically, you have the device has a listen interval, and that's mandated by the device. Your wireless infrastructure can't do anything about that specific listen interval. What you can configure is your DTIM interval. So your dynamic traffic information map, which is basically how frequently your network is going to be sending out information about buffered frames in those beacons. So if we can go to the next slide, please.
Yeah, can I just make a question? So this listen intervals that you're referring to are what you configure in the DTIM intervals, or I didn't get exactly what is a listen interval in terms of the 802.11 protocol.
Sure. The captures I've got on the next slide will probably help with that while I explain it. So just give you a little bit of information before we get into the detail. So it's basically just saying, my iPhone is saying, hey, Mr. Access Point, this is how often I'm going to wake up and listen to your beacons. Your beacons need to tell me whether you've got any information waiting for me to receive or not. So that information could be data, it could be a push from an email, but it could be an incoming Wi-Fi call. So if the access point knows that you're asleep for a certain period, it knows that it has to buffer that traffic for you. So as you can appreciate, with real-time traffic, such as audio, buffering is not really a good scenario. You need it to be real-time. And if some devices have really long listen intervals, which is basically just saying to the access point, be quiet, don't talk to me for a minute, I'm having a nap for a few hundred microseconds, and then I'll wake up again, have you got anything for me? And the access point was going, yeah, I've just received all this information for you, but my buffer's full up already, I had to discard it, and then your call has just dropped. So there's the challenge there with having devices with long listen intervals are more efficient with power saving, but there's a greater chance that they're going to miss some frames that are intended for them. So this capture that's up on the slide, the top one there is from an association request of an iPhone 8, and down under the frame decode, under the 802.11 wireless LAN parameters, every device should specify its listen interval. So when you take that hexadecimal 0014 and convert that into decimal, it's 20. So that's saying 20 beacon intervals. So let's assume that by best practice, you've got the default beacon interval of 102.4 milliseconds configured on your Wi-Fi network. It's very rarely that you should have to configure a different beacon interval, but that's a whole different discussion. So let's consider 20 times 102 milliseconds actually works out to be 2 seconds. So that's basically just saying when your iPhone is in sleep mode, there's an up to 2 second period that it actually might miss traffic that's designed. So if you just happen to have an inbound call in that 2 second period, and if the access point buffer doesn't handle that traffic, or the actual other party that's calling you in for some reason can't handle that delay, your call's not going to make it through, and you're going to get a missed call notification, and you go, oh, well, my phone never even rang, because it didn't have a chance to because it was asleep. So if you just click one more time, please, you'll see the highlight on the Samsung one down the bottom. So the Samsung Galaxy S9 listen interval is only 10 beacon intervals. So that's where you have to be careful. It's like, is your device more energy efficient, or is it going to be more susceptible to potential missed inbound calls? So it's just something to be aware of, and I'm extremely grateful for Mark bringing it up in his presentation last week, because I saw the light bulbs go off in a lot of people's heads when it's one of those things that's not really considered for voice over Wi-Fi applications, but it can have a big impact on your quality of experience on those devices. Any questions on that before we move on? Because I know that's a bit of a deep dive into that topic.
Tiveram uma pergunta também, se quiser falar em português, a gente traduz aí, então.
No?
All right, let's move on. But as I mentioned, I highly recommend checking out Mark's presentation when it comes out on the videos because he goes into some fantastic detail. So next, what we'll start to discuss is the security involved in actually setting up in the Wi-Fi call. So you might remember back from the diagram, the block diagram that had the components that make up a smartphone to carry a Wi-Fi call or LTE call. It said it gets wrapped up in IPsec before it goes over to the Wi-Fi. So Wi-Fi calling uses encapsulating security payload, which is ESP, and it actually uses IP protocol 50. So that's one big consideration that we need on our enterprise networks because, as you probably know, from an enterprise network going from your private IP address space to the public, you're going to be NATing a lot of your connections, probably all of them. You can't NAT IP protocols. So how do you get around that? You use NAT traversal. So there's quite a few services that do use NAT traversal, but basically NAT traversal is a process that takes an IP protocol packet and wraps it up in a UDP packet. Wraps it up with a UDP header, so then you can NAT it. So NAT traversal for ESP for Wi-Fi calling uses UDP port 4500. So there's actually a bit of a discovery that happens both ends, so your smartphone, as well as your Wi-Fi infrastructure and your firewalls and everything in your side of the network, as well as the carrier side and the EPDG side, need to support NAT traversal. So there's a discovery process that actually happens, which we'll cover in the next slide, about where the device and the gateway does a NAT traversal discovery, and that uses ISOCAMP to do that. So once they've gone, yes, we can do NAT traversal, the actual authentication that takes place for Wi-Fi calling between your device and the carrier can use multiple different methods, but typically it will use EAP-TLS. It's using credentials from a certificate stored on your phone. It's very similar to Hotspot 2.0 authentication. So your carrier could require the use of EAP-TLS, it could be EAP-SIM, it could be EAP-TTLS, or it could be doing something like EAP-PEEP. That's where your carrier might require an actual application where you would input your carrier's account credentials, so Stephen Cooper at Telstra.com, and then my password, and then that's how your device would actually authenticate for Wi-Fi calling. So that's very carrier dependent. That's where hopefully those examples of the Telstra and Verizon and AT&T links that I put up in the previous slides would actually tell you, what the carrier requires your device for authentication. Hopefully it would be nice and seamless and easy, just like what Telstra has. So once that's actually all established, it uses SHA-2 encryption, which is good, nice and secure. So if we could please go to the next slide. And what we'll take a look at here is just some frame analysis of the actual Wi-Fi calling tunnel setup. So at the top, if we click there on the top, we'll see a highlight there of where the phone actually tries to reach the carrier gateways. So what we have on the source on the left-hand side, the 192 address there is my iPhone. And based on that carrier config that has been pushed out to my phone already knows the IP addresses of, or how to resolve the addresses of the EPDGs on the Telstra call. So those are the destination addresses that you see, 122.17.148. It's basically trying all of those, but you can see on the right-hand side, there's quite a few retransmissions and duplicates happening there. Something's just not quite right with contacting those gateways. So the phone is constantly just trying again. And then we see down in sequence number 755, if we click again, the next highlight there, it's coming back with a server hello. So that's one of the gateways responding back. 17.248.219.12 has responded back with a server hello. So if you could click there, please, it'll highlight it. And then if we click again, we'll see the next phase, where this is where the certificate exchange happens. So you can see there in the info on the decode on the right-hand side, you can see certificate status, server key exchange, server hellos, and you've got these a handshake happening between the iPhone and the carrier there. And just notice the whole time it's doing this, it's been using TLS, and on the destination ports it's actually been 443, or the source port has been 443, which I don't have the source port column on there. And then right down the bottom, if we click again, we'll highlight where it's actually switched over to being established with an ESP protocol. But you'll see the destination port is 4500 because it's using that traversal. And then if we click one more time, we've got just the highlight there. You can see in the SSL information, we can confirm that it's using TLS with elliptical curve Diffie-Hellman exchange with SHA-256 for the encryption there.
Hey Stephen, there's a question.
Sure.
Do you have any problem with package fragmentation? I mean, you have to set up NTU or NSCS for that?
Sorry, was the question around fragmentation?
Yes.
Yes.
So I've not, myself, I haven't analysed that to that greater extent, but that's a really good question. So I think it would be similar to any other, voice over IP protocol handling fragmentation. Definitely a good question, food for thought. So might have to research that one and come back to you on how it handles fragmentation, because I haven't seen any information on that. But there is a document that I've found that we might better reference and have a look and see how that's handled.
Okay, but regarding the packet size, it's common to be small, or it's the big packets.
Voice packets are small, right?
Yeah,
Voice packets
common to be
are small.
But I'm not sure about that because of IPsec and that thing.
Yeah. Well, you can see some of the certificate exchange ones there are 1,550 bytes, so they're quite large. But once you see it's established down the bottom, it's 1570. So I don't have any other captures open at the moment where I can look at more of the call, but you'd actually be able to see, whether it's a consistent packet size or not, and whether it's fragmenting there. I'd have to have a look at the capture a bit further and just see if the fragment flag is set. That's a good question.
I have to tell you, Stephen, that we faced a couple of challenges in some of the customers that are here, in fact, in terms of fragmentation with CapWeb and passing over firewalls. So that's where the question came from. So
it's a really good question.
Yeah.
Yeah, it's definitely a big consideration. All right, next slide, please. Thank you. So this is just highlighting again, we've got the ESP packets there. You can see that the length of the packets there is varying quite a bit. So that is actually a call capture that I've got going there, and you can see that it changes. You can see the signal strength is changing. You can see the data rate is fluctuating up and down because I was actually walking around as I did that capture. And you can see the packet length does change. So, but yeah, the question is going into the detail about fragmentation. So I'll have a look into that later on.
So,
next slide, please. I'm just conscious of time here, so we'll try and get through the next couple of slides fairly quickly. So this is where we start to discuss some best practices which do overlap with a good voice over Wi-Fi design. So a lot of the implementations that I've seen back when I was at Dimension Data with customers, even just discussing with peers and other people, it's where it's quite surprising the number of people that have been working with wired and wireless voice over Wi-Fi for plenty of times, whether they're using Cisco Voice or something else. And they have everything set fine for QoS and everything's marked properly through, but then as soon as a new application like Wi-Fi calling pops up, they completely forget that they've got to consider this new application and making sure it's marked for QoS. So it's definitely something to keep in mind. So we have the typical RF considerations around access point placements, making sure you've got adequate primary and secondary coverage, whether you're going to be using Wi-Fi calling on particular bands or not. So that's quite a challenging one, because I've actually seen a lot of requests in customers for their guest networks to support Wi-Fi calling, or even BYD networks to support Wi-Fi calling. And those customers have chosen to have BYD and guest Wi-Fi as best effort on 2.4 gigahertz. So that's going to definitely impact your ability to provide a good experience with voice over Wi-Fi effectively on 2.4 gigahertz. I know most people would prefer to put it on 5 gigahertz because you have a lot more capacity there in terms of channels and less contention. So speaking of channel plans, if you're not already doing voice over Wi-Fi, maybe your data network is working rock solid with DFS channels enabled, but as soon as you run into DFS challenges with voice over Wi-Fi, that's going to cause a lot of issues with your handsets dropping off and changing channels to avoid radar and DFS events. So fast roaming optimizations, again, this comes back to device considerations. So you can enable this on your Wi-Fi infrastructure, but every device is different. So luckily, iPhones, they support 802.11k R&B roaming optimizations, but Androids don't always support them, and certainly the same can be said for different laptops as well. Every device is different, and that's where it comes back to that discussion about listen intervals as well. So make sure you know what capabilities your devices support in terms of channels, data rates, roaming optimizations, listen intervals, and that sort of thing. So another big key point there is checking how do your devices roam. So that's not typically something that device manufacturers or vendors will actually publish. Apple do provide some information about how iPhones and MacBooks roam. I know there has been some documents about some Android phones as to how those devices make their roaming decisions, but the best thing you can do is actually test it for yourself. So you need to see and figure out on your own networks how your devices are actually going to roam. And you also need to consider latency with roaming as well. So any voice over IP network needs to have a round trip latency of no more than 150 milliseconds, and that's extremely crucial on Wi-Fi, especially when you have roaming latency in consideration there too. So if we go to the next slide, please. So further considering your design from a capacity and quality of service point of view, it's actually quite surprising that, talking about the fragmentation side of things and looking at those packet sizes, when you've got a voice over Wi-Fi call happening, if you're using codecs such as, G722 or G729, they're quite light. They're only 30 to 60 kilobits per second, but Wi-Fi calling is 100 to 120 kilobits per second per call. It has a lot of overhead from the ESP encapsulation that it has, but it's actually quite heavy, similar to like what a Skype call would be. So that's something to keep in mind in terms of capacity. In terms of your infrastructure configuration and the capabilities of your infrastructure, you need to consider, the number of calls per AP, concurrent calls, and not only Wi-Fi calling calls, but typical voice over Wi-Fi calls, Skype calls. If you're marking all of this traffic that's voice over Wi-Fi at the same priority level, you're going to quickly, reach your capacity for that number of calls at that high priority queue. So you need to make sure you've got things, putting some Cisco terminology out there for configuration, platinum QoS, seeing whether your devices support WMM. If your devices don't support WMM, then you're not going to have a lot of luck being able to mark Wi-Fi calling traffic properly. So there's a couple of captures on the right-hand side, just showing, that the Wi-Fi calling traffic comes through with user priority 6, or it's going to be marked to access category voice on the Wi-Fi side, and on the wired side, it's going to come through as DSCP EF, or 46, expedited forwarding. So that's where you need to make sure that your wired network, as well as your WAN, has the QoS markings for Wi-Fi calling marked properly too. Another point to consider, especially with Apple iPhones, going back to the BYD scenario or even corporate managed devices, another thing that has caught people out is when they're deploying configuration profiles to iPhones using Apple Configurator, is you actually need to make sure that you whitelist Apple audio and video calling. That actually is applicable for Wi-Fi calling as well as FaceTime audio and video. If you don't whitelist that in the Apple Configurator profile, Wi-Fi calling won't mark the traffic properly at all. So, We go to the next slide, please. So if we click through here, we've got a few examples of some vendors which have got some great documents here on Wi-Fi calling. So a lot of these vendors have great voice over Wi-Fi deployment guides and best practices, but they do also have deployment guides and white papers for Wi-Fi calling as well. So we've got Cisco Meraki, Aruba, Ruckus. They also have some great information on there. So I definitely recommend checking out those links. And that pretty much brings us to the end. So we've got the final thank you slide there. So if anyone has any questions before we wrap up, feel free to ask them. Otherwise, you can reach me on Twitter and ask any questions there.
Stephen, I do have a question for you. So,
sure.
In regards to the firewall, whenever you have to configure an open port, ESP, UDP, whatever, do you need to configure it as an outbound to inbound, or just inbound to outbound? How does that work?
Typically, it would be outbound, and you set it as established. So the firewall would know that anything that's for part of that established connection, the return traffic inbound, it would allow it through. So most firewalls would support that these days because it's going to be something that's initiated from your device end.
Yeah.
It's never going to be initiated from outside. So as long as you're now allowing it outbound for an established connection, it'll go out through your firewall, and your firewall will detect that established connection coming back inbound, and you shouldn't specifically have to allow anything back inbound if you've configured it properly.
All right. Thank you.
No problems.
Hi, Stephen. Another question.
Hi.
It's regarding path MDU discovery, right? Is a feature that you don't need a fragmentation if it is deployed on the smartphone, right? So did you hear about path MDU discovery on the smartphones, just in a way to avoid fragmentation and in order to, to get a better experience with calls? Did you hear about?
Sorry, I missed that. What discovery were you talking about?
Path MTU discovery.
Right. Path MTU discovery. Okay.
Yeah. It's a one feature of workstations and just avoid fragmentation, right?
Yeah. So I wonder if that's supported. That's going to be a device dependent support for that. So that would have to be something that we'd look at whether the device supports that or not. Good question. Good question. I haven't specifically seen a lot of that with even voice over Wi-Fi, but I might dig a bit deeper and see if we can find that out for at least Apple iPhones and see whether they can support Path MTU discovery.
Yeah, because it will help you too.
Any other questions, guys? All right, Stephen, I know it's very late for you, right?
It's not too bad. 11 p.m. Yeah, it's not too bad.
So really appreciate your help and your support. I have personally a couple of questions for you, but I'm gonna do this on Twitter since we need to keep the time going here. We really appreciate it. Thanks a lot. Thanks, guys.
Thank you.
Thank you. Obrigado. Thank you very much. I know you've got some great speakers coming up, so you're in for a great day ahead. So definitely enjoy it.
Thank you, man. Take care.
Thanks.
Thank you very much.
Stephen. Thank you.
Bye, everyone.
Bye-bye.